Why is NP and NQ both being greater than or equal to 10 a necessary condition for using the normal model for the distribution of p hat? First of all, we have to remember that the distribution of p hat is very closely related to the binomial distribution. So we're going to first investigate how the sample size n and the population proportion p affect the shape of a binomial distribution. Then we're going to look at the mathematics behind the formula. First, we're going to look at an applet showing a binomial distribution in which p equals 0.5 and the number of trials n is 10. Notice that a normal model would be a fairly good approximation for this binomial distribution because of its unimodal and symmetric shape. But what if we changed the probability? If we made it much less, closer and closer to 0, notice that it becomes more and more skewed right. If we make the probability much greater, closer and closer to 100% or 1, notice it becomes skewed to the left. So it appears that when p is closer to 0.5, it's more likely to be able to be approximated by a normal model. However, there is a repair for a severely skewed model. So let's say we're very skewed here to the right. Now, if we increase the number of trials, notice that as we increase the number of trials, the shape becomes more and more like a normal model. Even though it is severely skewed to the right, this long tail is so very much close to 0 that the bulk of the data falls within a very unimodal and symmetric distribution. So if we have a very high probability or a very low probability, increasing the sample size can correct the problem. That is why both n and p are necessary in the formula to decide whether or not we should use a normal model. Now, why particularly do we use NP and NQ greater than 10? Here we're going to look at, I need to go backwards. Here we're going to look at the mathematics of the issue. If a distribution follows a normal model, we expect it to be unimodal and symmetric with its tails stretching about plus or minus 3 standard deviations from the mean. Actually, its tails stretch infinitely in both directions, but the majority of the data would fall within plus or minus 3 standard deviations from the mean. Binomial distributions show the probabilities for counts from 0 to n. So if this were 0 and this were n, we would expect the binomial distribution to be centered at NP, the mean of a binomial distribution, and have it 0 be about 3 standard deviations below NP and n be about 3 standard deviations above NP. So let's set that up then as a formula. So we're going to say NP minus 3 standard deviations. So the mean minus 3 standard deviations should be just greater than 0. And the mean plus 3 standard deviations should be a little bit less than n. So we're saying basically that they have to be in between. NP plus 3 standard deviations is just slightly less than n, and NP greater than 3 standard or minus 3 standard deviations is just a little bit greater than 0. So it's, but by the way, we're saying they're contained between 0 and n. So if we actually go through the math of this, first adding the 3 standard deviations to both sides of the equation, then we're going to square both sides of the equation, then divide both sides by NP. We get NP is greater than 9Q. Well, what is Q? Q and P are both probabilities. Probabilities are always between 0 and 1. So we know that Q has to be less than 1. It could be equal to 1, perhaps, but it's not going to be any bigger than 1. So we know that the number 9Q is probably less than 9. So if NP is greater than 9 times Q, we know at the most it has to be greater than 9, because otherwise this number would be less than 9. So to be conservative, we could say it's greater than 9. And then just to make it nice numbers, we say greater than or equal to 10 just because 10 is a nicer number. Now, if we go the other direction, and this would be a problem if we had something that was skewed to the right, because we would be concerned that its left tail was not at 0. So we see here that this is a binomial distribution that has n is 40 and p is 0.1. NP is not greater than or equal to 10, it's only 4. So you can see this distribution is not a good fit for a normal model. Okay, now if we look at something that is skewed to the left and has a high probability for a high p-value for the population. 40 times 0.85 is 34. That's bigger than 10. But if we look at the opposite, 1 minus p, or the q, the probability of failure, 40 times 0.15 is 6, and that's less than 10. Because what we're concerned is not this, the left-hand tail, but the right-hand tail doesn't go out far enough here. So we're looking at the opposite situation when we add 3 standard deviations. So let's see what this looks like. Here we would add the 3 standard deviations to both sides, we'd add and subtract NP from both sides, making this n times NP, n minus NP, factoring out the n, it would be n times 1 minus p, which is n times q. So now we're going to square both sides, divide both sides by nq, and I have 9p is less than nq, where p is less than 1. So to be on the conservative side, we would just say that nq has to be greater than 9, or nq, to make a nice number, is greater than or equal to 10. So for something with a small population proportion p that is skewed to the right, we would want to check that np was greater than or equal to 10. If something skewed to the left with a high p-value, we would want to make sure that NQ is greater than or equal to 10. So here's an example where P is 0.3 and Q is 0.7, sample size of 40. Both NQ and NP are greater than 10, and you can see that the distribution of the binomial is fairly symmetric and that a normal model looks like it would be reasonable. Now, these are all binomial distributions, but remember that sampling distributions of p hat from populations with these same population proportions would have the same shape, since all of the data values are just divided by a constant n. And when you divide by a constant, it does not change the shape of the distribution. It just changes its center and its spread. So the same condition applies. We can only use a normal model for the distribution of p hat if both np and nq are greater than 10.